Bonjour, hi everyone. I'm Renaud. I'm a CTO of co-founder of Preligens. So I would like to take a moment to welcome you here, either you are on premise or remote. Thank you for being here. Thank you for taking the time to talk a little bit about AI. You will see several presentations, and I may not have time to stay, but I'm really happy to see some faces in our new offices. Please try to keep your mask on when you are not in a talk position. And just a few recommendations. Do not wander outside because there is some batch to come in, so you will be stuck. And do not wander also in the other stair when you leave, because you may encounter some security or some alarm. So be careful. So just go straight to the outside. So I also thank all the speakers and Sikara for organizing, and I let the meetup begin. Thank you very much. Thank you, everyone.
Thank you, Renaud. Welcome to the 20th meetup Computer Vision. We are very happy to welcome you in physical. The last time the meetup was in physical, it was like 2 years ago. So thank you again, Preligens, for having us here. It's awesome. So today we have two talks. First we have Thibaut from Preligens, Tanguy, sorry, excuse me, who is going to present us how they build maps from satellite images. And then we have Claire from Norbert Health, who will show us an application of computer vision in the domain of health, and they will show us the products they build. So thank you again for being here, and the floor is yours. Thank you.
Thanks, Antoine. Do you guys hear me well on remote still? All right. So thanks you guys for being here. That's very cool to do that again in person. I wanted to talk to you a bit today about one of the things we're doing here at Preligens, which is automatizing the creation of maps, so think buildings and roads, from a satellite image. Why? Not just to show off and to talk about that, but I think that in the process we learned some valuable insights for you guys that could help you better do this kind of thing, computer vision, if that's what you're into as well, or just introduce you a bit to the world of mapping and satellite images, which is pretty cool. So, first, who used a map here today? Right, as expected, almost everybody. Why is that? Well, they are super easy to access, they're ubiquitous, they are full of valuable information, and they're just so convenient, you really get used to it. If you want to get from point A to point B, you don't have to know how to get there when you leave your house, you just use a map, that's it. And actually, maps are one of the oldest form of data visualization that have been found. Some 5,000 years ago, some ancient map in Egypt. So yeah, we've been doing that for quite a while, actually. The question is, let's imagine you're on vacation somewhere, and a friend say, hey, let's meet up there. But all you have available is this map, which is lacking lots of information. How would you get around? Well, not really easy. We kind of got addicted to the idea of having maps from getting around all the time. So when there are not maps available, which is definitely the case, we in Europe, in the Western world, having lots of them, Google Maps, Safari, it's not the case, everybody necessarily. So how would you do without a map? And more importantly, if it's not data that is missing, it could also be data that has been adversarially modified. For instance, that's what the government of China is doing with Google Maps. There is the satellite images data, but when you look at the map, you can see that there is some shift. The river here in the middle has been shifted here on the side. Why is that? Well, for some reason of data sovereignty from this government. So if you want to use Google Maps when you're traveling in China, it's very likely that you're going to have some issues. Now, let's imagine that it's not you wandering around in vacation, but more something like a government in a peace mission preventing some attacks of armed group on civilians, or any kind of critical application. Well, now you can see that having a map to get from point A to point B is an absolute necessity. And critical things is what we are doing here at Preligens. We are specialized on AI, especially on satellite images, for the defense and the intelligence domains. So we have a bunch of people doing that, very cool. I'm one of them. I'm doing deep learning here at Preligens. And the thing that I'm going to talk to you about, obviously, is not just me. We have a great team with great people. So yeah, we are specialized on AI and historically on satellite images, among other types of data. So yeah, we do a bunch of things. For instance, detecting vehicles, detecting aircraft, ships, all these kind of things. But here we are going to focus on the map product, so buildings, roads, and with a big focus on buildings, because that's the part that I'm personally working on. So, little question before we get further. What do you think is the resolution of a satellite image? So how many meters or centimeters per pixel are there in a satellite image? Who thinks it's about 60 meters for 1 pixel? Not many people. Who thinks it's about 10 meters for 1 pixel? Who thinks it's about 2 meters for 1 pixel? Who thinks it's about 50 centimeters for 1 pixel? Okay, so the answers are more on the high resolution side. My bad, it was a bit of a trap question. Actually, all of these are kind of true. It just depends on what hardware, what satellite you're using, and the choice of the resolution really depends on the use case. So, low, medium, high, very high resolution, that goes between 60 meters per pixel to 50, 30 centimeters per pixel. No, 60 meter, 50 centimeter. To give you a little example, here is the kind of images we could get at 60 meter per pixel. That's the Sentinel-2 satellite. So great for beautiful views of the sky on the Earth from far away. But as soon as you start to zoom in, not the most beautiful. But that's very useful for anything linked to monitoring the level of water in a region, ice cap, all this kind of thing. Another kind of image, this one is at 50 centimeter per pixel. And here we could see much more details. We could see actually the buildings, we could see actually the roads, the cars, all this kind of thing. So for our use case, making maps from satellite images, this is the kind of resolution we are going to use. So, why? Why do we want to automatize the creation of maps? The thing is, it takes a lot of time, a whole lot of time. So if you ask one person to make a detailed map of, let's say, a big city, well, it can take up to 2 years, which is an amazing amount of time. It's like tedious, it's a long process. So what we want to do is help those that create maps to do the same thing, but faster, so with a better quality and with more ease in a daily manner. Why is it difficult? Yeah, computer vision, that exists. We can do AI, deep learning stuff. Yeah, no big deal. Actually, 3 major things make satellite images for buildings a tough material. The first is, well, the objects, even at the highest resolution of 30, 50 centimeter per pixel, well, the objects are tiny. Here, for instance, this beautiful soup of pixel, you might see better if you're a bit far away, but this is actually a bunch of houses. And this thing here, that's a house. So it's quite challenging to teach a deep learning model to detect such a little object. Then, the quality of the images can vary. We can imagine you can have some clouds. Well, it's just satellite taking a picture from above the Earth. So clouds, rain, fog, sandstorm, anything, you name it. And maybe the hardest point is we want to have accurate maps, but we don't want to have a map that have too much information. And that's a very important thing. We want simplicity. We don't want useless information in maps. We want readability. So we want simple detections. Here in blue, you could see what would be a good detection in terms of per pixel accuracy. And in green is more what we want. We want something that's a bit more general, something that varies a bit from the ground truth. So that's a bit of a challenge. How you teach a deep learning model to be wrong, but on purpose? So I'm going to talk about a few things. First, the metrics. How do we tell a model it's good or not? Then the training. What kind of model do we really want to use? Is it more segmentation, object instance detection, this kind of thing? And finally, how to post-process the results in a manner that makes them look good. So, for the metrics, we have 3 levels of quality for validating a building. First, is there really a building here? We can have false positive, false negative. So first criteria, the detection. Then we can have a good detection, but the border might be 5 meters, 10 meters away from the real border of the object. That's vectorization. We want something that's close, let's say more or less a few meters away from the ground truth. And finally, what I was talking about before, the geometrical quality. So bad, good. And as always having a look at the data itself. What is in there? Is it any good? How does it look like? Very important to keep in touch with the data. About the training. So, the segmentation approach. Segmentation approach is we have a bunch of pixels, an input, an output, we have the same pixel, but for each pixel we give the probability that there is or that there is not a building. Object detection approach. We want to say, for instance, hey, in this box there is an object that we want. And ensembling, putting the two to work together. Do you think we use more the segmentation approach or the object detection? Segmentation, object detection, both. Smart. So yeah, let's see how it would look like. So here's an example of a satellite image. The one we had just before, so we see there are some bunch of buildings, some roads and everything. When we train a segmentation model on it, this is the kind of result we could get. So a prediction map for every pixel between 0 and 1. Black is there is definitely no building. Flashy green, oh yes, there is a building. And in between, maybe, I don't know. So, what do you think of it? Look good? Bad? Well, it's decent, it's definitely decent. There are lots of things that can be improved. For instance, would you be happy if you have that on Google Maps directly? No, why not? Because it's not beautifully cut, it's not vectorized, you have some uncertainty. You don't want Google Maps to say, hey, maybe there's a building here, maybe not, you could walk, I don't know. So, if we could vectorize it, but then say it's pixelized, not the best looking, weird vibes. So, if we zoom in, we can see an example here of segmentation map. This is good, we have complex shapes, but it doesn't really look nice enough to be put on a map as itself. Same here. Why is that? Well, there is kind of a tree in the way, so we can't do that. So it's great, accurate, but we could do better. And on the other hand, we have object detection, which is, we just put a box here. We assume that every building is a rectangle. Here is a building, rectangle, rectangle. Yeah, cool, that works. That works only if you have rectangles. So then the question is, okay, we have these two interesting approaches, both have pros and cons. How do we make them work together? That's the ensembling part. There are actually so many ways to ensemble different models. We have a bunch of papers, like we have a paper that's about this topic, how to make instance and segmentation work better together. So feel free to check it out. In general, lots of ways to do that. We could use one to validate the other. We could see if one is more included in the other than not, this kind of thing. So quick summary. Segmentation approach per pixel, complex shape, nice. You could have the ResNet model, Deep Lab model, or object, think, YOLO, RetinaNet, this kind of thing. Okay, now we have this. Now we have that. How do we get from there to beautiful polygons like that? Because yeah, that's the last step. Okay, we have our detection. Now we have to we want them to look beautiful. So how do we make that? The thing we learned is that post-processors are really key to have good results in a production context. That's really one of our key takeaways, is that you could have model giving the raw prediction. The raw prediction will never be good enough. You'll always have to somehow fine-tune it, tailor it for your use case. So let's see what we could have in terms of post-processors. This one, rather simple, but can be used in many different contexts. We have our polygon with lots of points, these pixelized points. Well, there are lots of methods to remove these points and only keep the meaningful ones. This approach, for instance, define a line between 2 points, and all the points that are within the margin are not significant, they get removed. Why is that interesting? Well, for that use case, yes, but in general, it can also be used for doing data compression. So you remove points that are not meaningful. Another thing, and this one I actually quite like it, is to use more traditional optimization methods to solve this kind of problem. What we have here, okay, we have simplified our polygons, look like that. So more simple, yes, but the angles are not quite right. We could do better. How do we do that? Well, there is a paper that came from the COGIT, the research institute from the IGN, the Map Production Institute. And this paper actually shows a very smart trick on how to make pretty much whatever you want as soon as you have the equations. So we just made some equations. Hey, we want the almost right angle to be really right. We don't want the points to move too much, to deviate too much from the truth. We could put that into some equations. Measure the delta of x, of y, measure the variation from the right angles. And we just have to put that in some traditional method, like the least squares, for instance. Does the job, does the trick pretty well. And here, you can see the result. Looks much better. Before, after. The good thing is that this method is not just useful in this use case, but there are so many other ways that you can use it. You just have to have a problem that can be expressed as some equations, and then you have it. You can just optimize it, and if it's work. Another post-processor, this one is more experimental, more here for the fun, let's say, but we are playing around a bit with some more data-driven type of post-processors. The idea is that machine learning models have evolved from being more rule-based to being more data-based. Now we have deep learning, but before in the 90s we had some more what we call traditional methods that are more based on the rules. This is kind of what we were doing before, embedding some logic in the post-processors, while we could also try to let the data speak for itself. And that's what we're experimenting a bit, just putting this out there. You take the prediction map, you want it to look more beautiful. By beautiful, I mean more right-angled, this kind of thing. Well, you could use some generative adversarial network, not because it's trendy and you hear about it everywhere, but it defines a loss on the data itself in a non-explicit manner. You don't have to say yourself, okay, I want that, I want that. You just let the data speak. Something we're just experimenting with, but how does it look like? Actually, we start to have good results. We can see here, that's the ground truth of the prediction map. Here, that's the prediction map that gets out of the first model. Then we turn the second model on top of it, so that here you can see that it kind of thresholds in a smart manner. You get the bit here that you wouldn't get with a regular threshold. So, just putting this out there, but in general, the more it can be data focused, the better. So, what have we learned here? Well, first of all, satellite images are cool, like really cool. I became quite a fan of it when I started working here at Preligens, and there are so many details, so many nice things you can see on it. It's really like data visualization on the Earth itself. And I don't know, I find it personally quite cool. Then the post-processors are really what makes the best results possible in production, because your model is likely to get some great results, but I have never seen a use case where just the model's output would be fine. Some post-processors are always somehow necessary. Also, talked about that a bit in the beginning, but the quantitative metrics is really what help us finding our way through the experiments. I talked about the detection, vectorization, geometrical quality. Well, we crafted these metrics ourselves, and in the end we used that as a compass to find the best tool, the best post-processor, the best parameters every time. Also, it's really important not to have only the quantitative metrics in mind. It's very easy to, let's say, overfit it. If your metric is the number of points per polygon for the polygon simplicity, well, if you just put rectangles everywhere, it works. The metric is better, but the model doesn't get better. So it's always important to get some distance, to put some distance between the model and you. Sorry, in the quantitative metrics and you. And finally, last thing we talked about here was the squaring method. So using least square method on some equation. And actually it just works super well. Personally, I think that a good data scientist, a good deep learning scientist, is not the one that will use the fanciest, the latest models, but the one that will use the best technique, the most adapted to the use case. So can be simple. If it works, perfect. If it works, it works. So before finishing, just a little opening like that. We started having more and more post-processors. We added some new tasks for some new issues, and the model got better and better. But in the end, it just brought a lot of complexity to the model and to the whole configuration, the whole post-processors. So a tool we developed internally really helped us to manage the configuration complexity. We call that our AI factory. We have a bunch of Medium posts about it. Feel free to check it out. And it's basically flexible, scalable framework to test at a large scale lots of post-processors, but also to do training of the models without too much of hands on the hardware. So just launching 10 execution like that. So we found out that having your own configurable, flexible tool to make your trainings and your configuration, evaluation is really what helped. The infrastructure really helps. It's not just the model, but the infrastructure that are around it have a big value. Some other things we use, TensorFlow, because TensorFlow. ValoAI is actually a MLOps tool that allowed us to kind of get rid of all the hardware part. We don't have to SSH on the machines to launch trainings one by one, but just copy, paste execution like that. And we use Docker for putting the models in production. QGIS is just something for visualizing satellite images. Other thing, but maybe less useful for your use cases. So that's about it for me. Hope you enjoyed this, and please feel free to ask any question either now or later with the beers. Thanks.
Thank you. Is there any question? Yep.
Just a basic question. What are the raw data given by the radar you're using? I mean, which data you're working on, and and what are the data basically outputted by the radar?
Well, that's a great question. What pour down by the satellites down to Earth really depends on the type of satellite. You have some constellation from AXA or Airbus that only do red, green, blue, so optical wavelength. You have some that do infrared. You have some that do radar, called synthetic aperture radar, SAR. So basically, it really depends on which satellite you're working with. We work a lot with the RGB and infrared as well. That's what the kind of thing we're using there, but lots of other frequencies are available. Some that are more targeted on the vegetation or the water overage, this kind of thing. So depending on the satellite, RGB, infrared, radar in general. Does that answer your question?
Yeah.
Great.
Have you started using any synthetic data, maybe to simulate like the cloudy or rainy weather that you showed us earlier?
Yeah. So for those who know, the question was, how are we using synthetic data? And the answer is yes. We are working with that. We have a research team that spent quite some time figuring out how to make it work and how to have the littlest shift of performances between the synthetic data and the real-life data. So yes, we use that, and we use it on some use cases. It works well, but it's quite difficult to find out how to generate the right images with the right amount of noises, how to make it look like a real image. But yeah, something we're doing, yes.
Okay, perfect.
Hi everyone, so I'm Claire Bichon and I'm here with Jonathan Platkiewicz. We are both machine learning engineers and we are part of the founding team at Norbert Health. So today the future of healthcare is growing, outpatient is growing. So indeed, hospitals are too often crowded, resource limited, and the work of nurses are getting harder and harder every day, with sometimes with new hygiene habits due to sometimes too invasive medical equipments. Before, the cardio services were keeping their patient 2 weeks after the surgery, and now due to a lack of space in the hospitals, they send them back home right after. So that's why we think that we need to be able to monitor patient health when they go back home after a surgery or whatever. And this is one of the reasons why at Norbert we decided to create a contactless monitoring device that you have here as well, with which we can get vital signs by simply standing in front of the device itself. And here are the vitals that we are measuring, like that. So this is how the dashboard of our device looks like. So here you can find 5 vital signs. Here you have the body temperature of the patient, and then the thing which is moving here is the pleth plot, and this describes the volume of blood you have in your arteries over time, and this is what doctors are looking at when they want to see if your heart rhythm is normal. And on this particular pleth plot, we are more especially looking at the 2 typical peaks that you usually have in the pleth plots. And from that, we can extract the heart rate that you found here. We also get the respiratory rate. And then by combination with other signal from other sensors, we also get the blood oxygen level and the pulse wave velocity. So in our device, we have a few sensors. We have actually an RGB camera, from which we get this kind of picture. We have a long-wave infrared camera, then it's the picture below. We also have a microphone and a millimeter wave radar. And with those sensors, we get some signal from which we can process and combine the signal to get the vital signs I was talking about. Some of those sensors give us the same signal, and this actually helps us to get better accuracy. And finally, what's also important to know is that those sensors aren't very expensive, and this is what allows us to produce a home device. And then today, I'm going to explain you a little bit more about how do we get the heart rate, more particularly from our device. So how does this work traditionally? So traditionally, what doctors use is called a pulse oximeter. So it's a device like that you put on your finger, and that will give you your vital signs. And how this works, so it actually sends two specific wavelengths through your finger, and on the other side of the oximeter, you have a photodetector that is looking at the absorption of those wavelengths through the arteries that are on your finger. And from that, they compute the vitals, the heart rate, the SpO2, or other vitals. And now, I guess you're probably wondering, how then do we get the same vitals by just standing in front of a camera? So what's important to know is that actually our skin color is changing every time the blood flows under it. And that's something that is very light. So the variation of the color of your skin is very light when just the blood flows under it. But the only case when you can see that is when someone is blushing. So I guess all of you already saw someone blushing. It's like your thick get red, or it's just that the vessel under your skin is dilating, and then the blood flows faster under it. And what's important to know is that this phenomena happen very slightly all the time. So the method that we're using to do that is called the remote photoplethysmography, and I don't want to repeat that. I'm going to call it RPPG. And the two differences there is with the method using the oximeter is that we're using the ambient light and not two specific wavelengths. And we're looking this time at the reflection through the reflections against your skin instead of the transmission through part of your body, which make the RPPG method a contactless method. So now I'm going to go through the steps there is in this RPPG method. So first, we have a camera, so we have the film of a face or someone. So first we do a face detection. So we do, we use YOLO particularly, but we do face detection. Then we do a skin detection. So we're looking into areas on your face where we can see the skin. And then we also do some, we do some thresholding because we want to get areas where we can actually get signal from. Because, for example, if you wear glasses or if you have makeup on, it's more difficult sometimes to get some signal. So we are also doing some extraction here. Then an important step also is that we reproject the RGB signal to the color space that's called LAB. LAB is better in this case because the lightness is apart the color, and the color is only on 2 dimensions. So it's better to detect small changes in color. Then we do some motion suppression because, like when the people is moving in front of the camera, this adds noise to the signal as well. So we have to get rid of that as well. And then we extract the signal. Then we do some filtering in order to get the right peaks of the signal, and then from the peaks we get the heart rate. And to go a little bit more again into the detail, here is the long formula for what we get from the RGB signal. But what's important here is mostly that the color signal is a function of the pulse signal. So the pulse signal is actually a heart rate, and it describes the variation of of volume of blood you have in your arteries. And basically, the RPPG algorithm is extracting this pulse signal from the color signal. So basically resolving this equation. And this equation have two big issues and challenges. First, we have to get rid of the sensor noise. Second, we have to make it linear. First, to make it linear, we do the assumption that the light change, so what we call illuminant here, is the variation of the light, but we say that the variation of the light is way slower than the variation of your pulse. And so we make it a constant, and which this means that then the formula became linear. And then to get rid of the sensor noise, we do some spatial averaging. So for that, and that's why I put this picture here that might look a bit complicated. So on the face, we actually split the skin area into small areas from which we extract the signal. So for each areas, we have many pixels, and we do an average to get one signal per areas. And then here, you see on the image all the little signal corresponding of all little areas on the face, and then we again merge those signals by doing an average. And as we get rid then of the sensor noise because it's not correlated spatially. And last but not least, to make this formula resolving easier, we do a reprojection of, so I told you the color space were LAB, and then the color was only on AB in 2 dimensions. So to make it 1 dimension, we reproject one axis to the axis that amplify the color variation, and then from that we can solve this equation. So in this project, we have some serious challenges. First, the work into the wild. So it's easier to make it work with only the same person standing in front of the same camera in the same room with the same lights. But it's something different to make it work when the people are a little bit moving, or like in different areas with the exposure, like in hospitals, can be different. Or like with different skin type, it doesn't work the same. So those are a bit challenging, and that's what we're working on as well. The other one is that as we're working with medical professionals and with patients, then we have to get a medical grade accuracy, and so in this project, accuracy is really a big point. And then we also encounter some engineering, of course, challenges due to limited compute, because as you see, it's a device by itself, so everything is embedded. So we have a limited compute, and still we want to have the better signal, and then we need a good quality image. So still on this challenge, I just wanted to mention to illustrate that you don't have to read all the slides. I wanted to say that first we were using a webcam, but and the webcam, like, the important thing is that usually the camera are made with some auto control, and this auto control, which is called chroma subsampling, is some kind of compression of the image, and this actually compress a little bit the color of the image, but in favor of the brightness of the video. And this is usually made for photography, but what we have to do, because we want to use it we want to use the camera as a measuring device, then we want to do the conversion between the raw image to the image that will give us the best signal by ourselves. So we had to redo this whole conversion. And so finally, I wanted to also talk a little bit about some other project we are currently working on at Norbert. So first, as so I said, we had a radar as well in our device, and this radar can give us some vital signs as well that are similar to the one we get from the camera. And so to get a better accuracy, we're working into combining the signal we get from the camera with the signal we get from this radar. So yeah, that's an interesting project as well. As we want to do monitoring in hospital rooms or people houses, we want to do we want to do a movement, position, and falls detection. And for that, so we are using the RGB camera, but this is something that's already existing. But what's interesting is that we also use the radar and the IR, the long wave infrared camera to do the same thing, so that we can do it even at night or when it's dark. And then another project that's very interesting. So in the current stack, we are doing the face detection with our RGB camera. Then we reproject the points in the long wave infrared camera. And from this camera, we get the data that we want from the long wave infrared. But we're also working into doing directly the face detection in the long wave infrared camera, so that we can get the landmarks, so the eyes, the nose, and the mouth points on both cameras. And with the same points on both camera, we can then do some stereo calibration, and then from that get the distance of between the patient and the device, and this is helping us also to get better accuracy and to know even more about the patient. And so this is us, the great team I'm working with. So our CEO, Alex Winter, is a seasoned entrepreneur. He has built many companies, and he's an innovator in computer vision and AI. Pat, our co-founder, has built all from scratch. And the great team you see here come from the best unis and companies, and we're also working very closely with some doctors from hospital in New York and in Paris. And finally, we are splitted, unfortunately, into two offices. One is in Brooklyn, so the one you see on the right. So it's a really interesting place because it's an old Navy yard that has been rebuilt into a tech hub. So it's really great place. And the other one in Paris is actually very close to here. And as you can see, so we just moved to our own place, and as you can see, we're having a lot of fun. And so, unfortunately, that's the end. But you can still ask some questions. I wanted to mention also that we are hiring, so we are looking for great talents, and you can find all our job description on our website. So thank you all for attending, and thank you for the warm welcome. If you have any question, then also I wanted to tell you we are willing to do a presentation, not the presentation is done, a demonstration with our device. So we bring everything here if you want to try it to get your vitals. It's here. And if you have questions, Jonathan and I can respond. So, any question?
Any question?
Yeah, sure.
Thanks. You spoke about your second project with landmark detection and then mapping that to the infrared camera. How do you do the landmark detection? Do you have on-the-shelf available models? Do you have some training? How are you tackling that issue?
You mean the landmark detection in the long wave infrared or in both?
In both. Actually,
we do the same. So first, on the RGB frames, we're using the YOLO V5 5 landmarks, And what we were doing to do the same in the long wave infrared is that we took actually the same model, but with different input size of image, and we retrain it on our data. Infrared data, and we get actually good accuracy. So we use the same model for both cameras. And what also we're looking into doing is that creating a model like the YOLO, but with more inputs. So we would like to input the RGB image plus the long wave infrared and get in output both landmarks and detection in both images. Yes.
How do you detect the breath rating? Does the breathing is detectable by the temperature camera, or is it the same process than for the heart rate?
No. So the breath is extracting from the place plot that you see. So the signal. From that we do. Band passant and band. We do some signal processing to extract, because so the big changes will be the breathing rate, and the small changes will be the heart rate. Maybe Jonathan, you want to add more about that?
Yeah. So what happens is actually you have two. As Claire say, it's on different scale. So breathing rate is typically I would say under 30 BPM, so beat per minute, whereas heart rate is typically 60 to 100 or more. So basically you do a band pass filtering, and then you can just separate the two rhythms.
Yes. Okay, so the second one is kind of first one. Those people accept the camera easily. So yeah, I forgot to mention that we're anyway working with investors in the US and in France, and we have two markets, one in the US and one in Europe. So that's something that it's easier. I will have to admit in the US, right? But that's something that's they accept it. And then our market now is more hospitals. So yeah, it's something that's easier in the US than in Europe.
Anonymous, right?
Yeah. It's sure it's anonymous. So yeah. So we exact. It's anonymous. So hello and thanks a lot for the presentation. You said that it was a challenge to get the medical grade degree certification. And at the same time, there were difficulties because of skin pigmentation, light condition. How can you be sure that this respects the medical degree and that your system works for everyone? Did you have intensive acquiring campaigns, or how did you reduce the bias of your model? You want to respond to that?
Yeah, sure. So first, part of the certification is to be able to get the whole range of skin pigmentation. So, for example, there was even a headline issue in the FDA, which is American medical certification, that say that there is a big problem with oximetry in terms of getting all the range of skin pigmentation. So that's and for us the way we do. I mean we are by collecting more data, we ensure that we get more diverse data sets, and so and then we can be more robust to this variability.
Thank you. More? Okay. Yes.
I know there's some requirements from the accuracy you need to meet for the medical side, but I guess you also need to be very fast because it's a critical application for some cases. But is it possible to do some? I mean, why? Is it possible to do some computation online on cloud, or is it too slow for your applications?
To check the
No, I mean to not use an embedded device and to do all the computation on cloud and retrieve the answer and then do the alerts system.
But so we do all the computation on the device, but it's embedded. So we can. That's our constraint in a way.
That's our constraint. So if we wanted to make it on the cloud, it would be possible and much easier for us actually.
Okay.
So in a way, that's part of our design. Like it helps us to be, like, for example, like in terms of like the data to be more restricted. So like we don't like we have less problems from anonymity, and then also it's it bypasses a lot of like technical challenge.
Mm-hmm. Okay.
I have two questions. The first one is, it is a medical device or not this one? It is medical device?
It's not satisfied. We're working on that.
Okay, it will be a medical device.
That's our goal, yeah.
Okay. The second question, no data is saved in the system? Nothing? Image or...
Data is not saved. The data is it's computed. I mean, all the vitals are computed on the processor, but then all the data are sent to the cloud.
Ah, that's something. Okay. And okay, you have a profile, for example, for a patient. You check and follow his status and the time.
So we have many features. So if we don't want to store the data, it's possible to just show it on the. So you'll see we have the display and the dashboard here. It's possible to just see it real time and then don't save the data. Then if we want to send and potentially notify doctors, that's something that's also doable. And if we want to store even like the identity and do some face recognition, that's also something that we could do. But you know, it's so we have different features and it's possible to. Depends what you want to do with the device and what depends of our clients. Yeah. Yes.
Thank you. Question about how it compares to connected watches, because I heard with Apple smartwatch you can measure also the O2. That's what I heard. And how would you compare it with smartwatches?
I mean, the smartwatch is actually a wellness device, so they don't go all the way to the medical certification. So really, like the way, I mean, our goal is to go to the medical certification and be a hospital like a tool. So that's the main difference, you know. And also, like I will say, you know, if you ask about that, like for example, for the Apple Watch, the technology is different. They use like ECG, for example, and the SpO2 they use like the classical oximetry, whereas like ours is this remote oximetry.
Yeah, and as you were asking for comparing our data, so what we use is that we actually, you'll be able to see on our dashboard, we also connected the dashboard to the oximeter, and we took a medical grade oximeter, and then we first, to test, we provide both at the same time. So then if you sit in front of it, like this will record your heart rate and your vital signs, and the medical grade oximeter will do the same, and then that's how doctor could check if it works enough for them and yeah, that's how we also get our ground truth. And if people want to try our demonstration, it's open.